Now let's just get consistent about signs, because my consistency, I wasn't completely consistent here, but I want to make a graph and talk about the results of this a little bit. Okay, so here's a circle, and here's a vector normal to the circle. So that when I'm aligned on the xz plane, the normal vector is the j vector. As I rotate to the 45-degree position, the vector becomes j minus I, quantity over the square root of 2. And when I rotate to this position, the normal vector is going to be negative I. If I continue around, I'm going to not, well, let's go ahead and try this, okay. If I continue around, you can't see the normal vector, but it's here, and you can figure out what that would be. Well, it's negative I, negative j, over the square root of 2. Here it's going to be negative j. Here it's going to come around to what? Negative j plus I, so it's I minus j over the square root of 2. And here, of course, we're back to, well, not back to, we have the normal vector is I. Here it's going to be what? I'm not sure I'm staying in the camera, but here it's going to be what? J plus I. And here we're back to the beginning when the normal vector is j. Okay. Not sure how well I kept that in the picture because the screen was behind me. But you get the idea. We rotate from here around to here, and the vector goes through j to negative I, to negative j, to positive I, and back to positive j. The vector normal to the plane. Okay, so if I want to use the vectors that occur as I go around the circle, rotating this plane about the z-axis, rotating the plane of the circle around the z-axis in the positive sense, where we're going from x to y and so forth, the right-hand rule would give us a thumbs up, which would indicate a positive k, so we do have a positive rotation. If we have a positive rotation, then here where the circle is in the YZ plane, now I didn't specify whether the circle is in the YZ plane having rotated just this much or having rotated all the way around here. Around here the normal vector would be positive I, but here the normal vector would be negative I. If I just want to think about the rotation from here to here to here, then I'm going to want to use the negative I. And that would give me a negative 0.02 Tesla meter squared. We were starting in the XZ plane, and in the XZ plane, of course, our flux was 0. Between here and here, we went to the plane x equals y, where we had the vector j minus I, which would correspond to the rotation from here to here. So we're in this position with this calculation. So we have flux 0, then negative 0.02 Tesla meter squared times the square root of 2 over 2, okay, and then finally negative 0.02 Tesla meter squared. If I put that on a graph here, and I've already got a graph, but I'm going to draw the graph that actually corresponds to this part of the rotation. It's going to have the same nature as this graph, but we're actually starting at 0, and then we're going to negative 0.02 Tesla meter squared at whatever time we reach the YZ plane. And in between there, we have like square root of 2 over 2 is about 0.71, about 71% of the negative 0.02. That's going to give us something like this. So that when we connect these, we get a curve that looks something like this. Now, if we continue around, we're going to go through, well, if we continue around from here to here, we continue around another 90 degrees, we're going to be back to where the flux is 0 because the plane is aligned with the the YZ plane. The normal vector is negative j and I dot negative j is 0, just like I dot j was 0. So we're going to come back up to 0 flux. And then as we continue around, okay, if we continue around from here to here, we're going to come around to a positive flux. And it should come as no surprise that positive flux is going to be plus 0.02 Tesla meter squared. And then if we continue around to our original position, we're going to come back down to 0 flux. So we're going to have this. So we have a nice sine wave. And you can verify that it's a sine wave. And we will actually, we'll solve a problem in just a little while where we let the normal vector just be a function of time and give it an angular frequency and analyze it accordingly. But rotating a loop in a magnetic field, or alternatively, if we rotate a magnetic field within a loop, we're going to get a flux that looks something like this. We're going to get a sinusoidally varying flux. And just a little preview, the voltage that we get around this loop is going to be the time derivative of this flux. So that if we do just the derivative of this, well, derivative of a sine or cosine is going to be a sine or cosine function. We're going to change the amplitude, and the units of the amplitude will become voltage. So we're going to have a sinusoidally changing voltage, and if we run this through a simple resistance, we're going to have a sinusoidally varying current. If we run it through a circuit with a resistance and a capacitance, it's going to be somewhat different. Or resistance and an inductance, it's going to interact differently in ways that we'll see very soon.